Yeah, I was at Twitter until last Friday. I'm now doing Clojure again, which I'm very, very happy about. So I'm going to talk about Cascalog, which is this open source library I've been working on, I guess on and off for 2+ years now. I also threw some buzzwords in, datalog, realtime, just to fire you guys up. They do have to do with what I'm talking about. I used to be a Clojurist, went to Twitter, sort of was hoping that it was fully embraced. I was pulled off into the evil world of Scala and have been working with types for some time now. Now that I'm out, I want to use the tech I used to use, but it was completely based in Hadoop and MapReduce. It was all this big data stuff. And PaddleGuru is like race management for paddling sports, and it's not big data yet. It's not going to be for a long, long time. Right. So the solution are like, preach that or make Cascalog work for smaller data and for other models of computation that aren't Hadoop. So that was the goal of this sort of almost autistic rewrite of the entire code base I did over the last couple months. And I just want to take you guys through a few pieces of that new code. So we're going to talk about today what Cascalog is, for those of you who don't know, and just kind of going through some of the ways, some of the types of computations you can do on your data using this logic programming model. It's quite different. I'm actually stoked to be at the Clojure conference where like logic programming is not scary, but monads are, but it's hard to keep track. So why logic programming? You all know already. It's amazing. The analytics story I think is really, really good in Clojure. A lot of the tooling's amazing. I think this level of abstraction has been fantastic for working with data at Twitter scale, but within sort of, we've seen a lot of the applications of logic programming, even in the browser, with some of the work David's been doing, and yeah, it's just badass. And then you can just tell people you're coding a web apps in logic, and it's so good. We're going to talk about how the compiler works, how Cascalog compiles this data log graph down into a logical graph, and then eventually down to Hadoop. And some alternative for compilation targets that this new rewrite will support. We can do sort of more interesting things now by being a little lazier about the way the compilation works. And then what's next? And David, I see you there. The real goal of my talk is to make you smile. I see. And we're done. Okay, what is Cascalog? What am I talking about? Cascalog is a data log DSL in Clojure that helps you write, until now, Hadoop jobs, but primarily big like ETL or analysis jobs on many like large logs or streams of data. So some of the questions you might be able to answer more easily using Cascalog would be, go find me all the users in the Northwest who like to paddle, who are under the age of 30, who do this. You express this in a logic language as just facts about your data set and let the system figure it out. In raw Hadoop, you're sort of imagining key value pairs and shuffling your data around. And you can reuse the stuff, but nobody does, and it's really horrible. So yeah, you give the system facts, and it tries to write these analytics pipelines for you. And if there are better ways to do things, the system can go optimize for that. You don't have to worry about it. A lot of these optimizations are really systems problems, and with a bit of knowledge about your data, the system can tune quite a bit. Because of Hadoop support, you can do the sorts of things we'll look at enormous scale. I've never actually worked at petabyte scale, but I think it's possible. Gigabyte, terabyte. Yeah, you're effectively not constrained, and if you think this way, you're setting yourself up for growth in the future. The problem is that it's been Hadoop only until now, so we've got this great scaling story, but like often you want the scalability without the Hadoop. You just want to be sort of guarded against the future. So we want in-memory modes. We want to be able to do maybe real-time streaming, things like that. So let's see some code. This is what You want to see it again? All right. I don't know what this says. This might be like a Chinese tattoo that says like "fuck off," but it's Braille. I don't know. This is what Cascalog. This is what Cascalog looks like. We're going to go through like exactly what this means, but effectively this is a little logic program that's embedded in Clojure, which tells the system how to calculate, based on some generator of like sentences, how to calculate word counts. So this thing itself is not doing anything. It's just a declarative structure that Cascalog can go turn into a Hadoop job down the road. There's also a serializable function in there. It's pretty cool. That's important to generalize this thing. But yeah, this thing turns into a Hadoop job, but there's nothing really Hadoopish about it. So this is how you do the same sort of thing, the MapReduce word count in straight Clojure. I know there's more elegant ways to write this, but this just sort of models what Hadoop would be doing under the hood. Effectively, what this word counter does is takes in some sequence of strings, map cats across them to split them up into words, adds like a count onto each word, so you end up with these pairs, and then does a group by the key and adds together all of the values. So it's very sort of, you're writing in here the steps that you need to take. You could pull some of this out into helper functions and make a nicer DSL over top of it, and many people have done that, and it's great. But this thing will go count words. It's not easy to generalize this to sort of other types of aggregations, but it does the job. This is what that same thing looks like in Cascalog. We'll go through this in more detail in a minute, but effectively what you're doing is just telling the system 3 facts. You're saying some generator comes in, something that can sort of produce tuples. This second line here, this like gen, says there's some concept of a variable called text, and we're constraining it to have to come from the generator data set. So this thing will sort of, the system, what Cascalog does is takes these constraints and tries to solve them given all your inputs. So when you say text comes from generator, that takes like every possible text that could happen, constrains it to come from this one data set. Then you're constraining a new free variable called word to be the result of like splitting text into words. So this one kind of maps to the Clojure, but it's fundamentally like a different way of thinking. You'll notice the split and the generator are out of order. Split showing up before there's anything to work on, but the system will figure it out. For smaller stuff, it's still compelling. It's still competitive with the Clojure, but for more complicated jobs, like this one, which is one of the first Cascalog queries I wrote, actually, it's hard to compete. What this is doing, some of the first work I did in Cascalog was satellite data processing. So what this thing does is takes a generator of like NASA MODIS satellite data sets and pulls them apart, like extracts metadata, puts them into a thrift format, like does all sorts of aggregation. It's many MapReduce jobs, eventually kicks out sort of this normalized chunk of data that we can go store long-term in our system. And if it was bigger, like it'd be beautiful, it'd be clear to read, but this is sort of the logic, and you can go look at this thing, and if you know the Cascalog idioms, you can understand the facts that are being used to generate your data. Okay, so quick overview of what a Cascalog query is. They all have this shape. It's very, very consistent and easy to read once you're familiar with it. Everything is, Cascalog's first class structure is a subquery. It's declared with this little left arrow. And what those look like is you give some sequence of output variables that you are promising to sort of create with your constraints, and then a list of one or more predicates or constraints on those things. Those constraints can be generators, they can be operations, they can filter, they can be aggregations. At the end of the day, the system will figure out what to do and pick the ones that it needs to go generate your output variables. So in our example, the word count, the subquery said, I promise I will create constraints for the variables word and count. And the logic variables are prefix of the question mark. Anyway, here's a generator. Text is like coming out of this thing, or alternatively, you can say the text variable is like constrained to come out of this generator. This one's an operation. It's saying basically you can make words by finding every possible solution to splitting the text. And then, I don't really have a good metaphor actually for like where aggregations fit into this, but effectively what you're doing here is saying, I want to go create like every grouping on word, go figure out like what the count is for that particular grouping. And then this subquery itself is actually a generator that can be used in other subqueries. So you can lock away logic and sort of build up these very, very complex things. You don't really know where text came from. You just have a generator which could be some Hadoop structure or some other computation that you haven't actually made yet. So you can make these like enormous data graphs without actually doing anything, which is something I'm quite interested in. All these predicates have the structure, some operation, some set of inputs, input variables to the function or so, and then this little keyword, and then the outputs. These are just data structures. There's nothing sort of special going on. At the end of the day, The subquery macro is just a little sugar over turning the question mark prefix variables into strings. So yeah, you just give the system a bag of these and it goes and figures out what to do. So word count, as we saw before, it's just a function that returns one of these. They're first class, you can pass them around, you can go construct them. We're taking in the generator and then defining the subquery which creates word and count. As I said, the return value of this is like a totally valid generator in its own right. So let me show you if I can do the Emacs switch. I can't see it on my screen, but I think it's going to work. Let's see. There's the mouse. Oh, yeah. OK, so here's the word count query we just looked at. And then you can go say, sorry, I'm trying to type by looking at the screen. Oh, God. Here we go. So you can see at the bottom, maybe, this is the Clojure version. This is the Cascalog version. It's the same code I just showed you. And if I run this in the REPL, that's a Hadoop job that just launched in the REPL and generated, well, word counts for like 2 sentences. But it's still a Hadoop job, and it worked in the REPL. It's amazing. Sort of aside, when I showed up at Twitter, had a REPL open on the Twitter job tracker and would play like this to show people. And it fucked up at one point and like hosed the whole cluster for the entire night, like from my Emacs console, just doing this. Nobody knew it was happening. It was a victory. OK, something a little bit harder. Harder for me to think about anyway. I tried to write this in straight Clojure and immediately gave up and worked on my slides more. Find the full name of every person following someone under 30. This kind of looks like SQL, and in fact, they're quite related, given these tables. So I have an age table of person, comma, age. I've got a follows table of follower and person, and then I've got this like full names mapping. So if you have all these things, the question I want to ask of Cascalog, this example I'll show you is, let's find the full name of every person who's following someone who's under 30. So you can kind of feel the constraints, like mapping, in here. Here it is. We've got full name that we're promising to create. That's what we want, as we said, as the problem statement described. Each of our generators can produce some set of logic variables. So follows produces follower and person. It's just a statement about what we have. Full names produces follower and full name. Age produces person and age. And then we have this final constraint that age has to be less than 30, right? So, and then this like little option saying at the end of the day, we only want the distinct outputs. Now, there's no join going on here explicitly, but implicitly, because we named different variables the same thing, the system will figure out kind of possible solutions given that these are the same entities. So, as we said before, these are all generators. This is like a little aggregation option, and this is a filter. But the ordering doesn't matter. We're just telling the system a number of things and saying, figure out what the full name is. And the results of that are, I'm not going to do the REPL again, but the results, sure enough, are just these 5 names. Actually, what the hell? Oh, let's do this. OK. We've got all these data sets. I actually want to show you this because you can do some extra cool stuff. OK, so that's the following query. If I run that, sure enough, I get those results. What's interesting is you can actually, I don't know if you can see this, you can actually just inline constraints. So we can say, who's following someone who's 28? That's an interesting question. And then we can run those in parallel. So this is the output of both of those run in parallel on Hadoop in the REPL. So we have all of these, and then here we've got the first one was slightly fewer because it's only people 28. This is people under 30. So it's really, really easy to go play with this stuff. You can take existing code and just make functions that take these little filters and return them. It's no problem. It's really kind of a beautiful way to express logic. The problem is the set of abstractions that it sits on. Like, so yeah, as you go up the abstraction layer, the emoticons become happier. This is actually, it's kind of a kinky Hadoop elephant. I don't know where. I don't know if this is official or what, but I liked it so much. Anyway. Hadoop's at the bottom. Cascading is this Java library that sits over top that makes it a little easier. Clojure and Cascalog are on top of that, and they go build these MapReduce jobs. But at the end of the day, like, all you're thinking about is the Clojure. There are hooks to get underneath because we can't express all of the subtle, arcane configuration options that Hadoop has to offer. But for most things, you can stay at the top level. So I think there's what's the Hindu legend about the world riding on an elephant's back? Cascading does the same. And the question I had doing this rewrite, and that's kind of what this talk is about, was, is there anything about the data log that's specific to Hadoop? Or could we target other compilation platforms? Spark, for example, lets you do the same sorts of things we just looked at, but it holds everything in memory, so you can do these really nice iterative computations. Storm doesn't have a logo, but this is a Storm. Storm is a real-time processing system. You could imagine, like, using that data log graph as a constraint solver, which, given some time window, is operating on your tuples all at once. So as things come through, if it's a person who's following someone who's less than 30, kick it out into a future queue or write it into a key value store. Like, these are things that make sense, but the older version of the library, everything was coded it sort of eagerly compiled into Hadoop, and it was very hard to break that boundary. It's an open source project. I've maintained it for a while, and I figured that, as I was sort of suffering in the Scala land, I did like it. I could go ahead and just, push a pull request to the code that rewrote everything, and it turned out, the other maintainers accepted it. And so we have this new compiler that I'll talk about in a minute. I did want to say, because it's open source, a lot of people are using this now. It is out there. It's useful. It's on Hadoop, including the Climate Corp, which was acquired for $1 billion, primarily because of this technology, I think. It's unclear. I actually did find the article about the acquisition and Control F for Lisp and nothing, and then for Clojure and nothing, and then Cascalog. So, it's a sad moment last night. But yeah, open source project, you should all use it. And quick aside, why data log? Like, why should we think this way? It looks useful, but is it really that helpful when you get to real stuff? And the reasons I would say are, one, your users will be happy. Yeah, anyway, I had to get this in again. I've been reading this, I'm sort of appealing to authority here. I've been reading this book by Fred Brooks called The Design of Design, which is fantastic. He wrote The Mythical Man Month, and every page is just, the guy's had a long, battle-hardened life designing things. So his comment that I'll appeal to is, when you specify something to be designed, tell what properties you need, not how they are to be achieved. This was about clashes between, sort of design requirements that humans have from each other, saying, I need you to solve this problem, I need it to be using Hadoop, I need this. It sort of inhibits creativity in a very painful way. I've started to come to the believing that it's the same way with how, the computer works. As with these massive data pipelines, you don't want to be micromanaging how your system runs, given that there's still this arbitrary abstraction layer of Hadoop, right? It's still key value pairs on MapReduce. So to sort of try to pretend that you're doing sequence operations and fit into that paradigm is okay, but you're going to fuck it up. And I think of it as micromanaging your data. And often what would happen at Twitter was, we write in this language called scalding, which is sort of looks like the Scala Collections API, but turns into Hadoop. Some poor young engineer would write a job and realize a list in memory instead of taking off the front in advance. And one of the graybeards would look at the code and be like, why the fuck would you do it this way? What were you thinking? I don't know. It's these sort of decisions about how the system does its business are hard to anticipate, and especially when you start switching compilation platforms. For a lot of your logic, you want to be as high up as possible so that Storm can figure its thing out, Hadoop can figure its thing out. You can jump back down if you need the specifics, but at the end of the day, stay high level as long as you can. I think that, we get a lot of leverage here out about working in terms of properties of our data. I think the Scala guys are so jacked up on types because when you know they are. When you know the algebraic properties of your data structures, I would say you can do a lot of reasoning at the systems level. And this is the same sort of thing. We have the power to do that about our data at the application level. A lot of the schema stuff yesterday was really exciting because I think you can kind of get the best of both worlds. You can actually start to talk about the algebraic properties of your data and, anyway, that's sort of next steps. Okay, how does this thing work? Like, I didn't actually know this till I rewrote it, so I may have screwed this up, and I'd actually, if anyone who knows how to write a compiler will like tell me I fucked this up, I'd be very, very happy. But we're going to talk about how my version of the Cascalog compiler works. I think it's pretty reasonable. So this is the kind of subquery. What we want to do here, what Cascalog does is takes a subquery that looks like this and turns it into a logical graph that is doing, effectively can be turned into one of those Clojure stream transformations or Hadoop land or whatever. So the way this works is, like I said, we want to satisfy this full name. We want to basically like make a new generator, which generates full name. And we've got these 5 predicates to work from. So what the Cascalog compiler does is just takes all the facts and starts to pull out facts that it can use immediately. The first things it can use are these generators. So there's 3 of them in here. The follows generator produces follower person, blah, blah, blah. We talked about all that. So those are out now, and so we'll cross them off from the predicates list. They've been dealt with. Again, it doesn't matter what order those are in. Now, every one of these generators has access to all the other predicates, and what they do is try to eagerly apply operations to their, like any operation that acts on variables that they contain starts to get applied. And they can, pull those out of this bag. In this case, the only operation left is age. It's this filter. Age has to be less than 30. And the only one of these guys that has age is that one over there. So I spent a long time in this slide, by the way. This is like keynote magic. So age has to be less than 30. We can't operate directly on constants, so we insert this node in the graph that inserts 30 into the flow. And you'll see now I've got person age and temp1. We've got this temporary variable that's floating around as well. And then the filter gets applied, so that stream gets cut down. Now there's no other operations to apply except this final aggregation. But like I said, you've got to end up with one thing. So we have 3 here now. So what Cascalog does, what the compiler does, is start searching for common fields that it can join on. So in this case, person is shared between all 3 things. So the system will, in an attempt to sort of further keep going, trigger a join. At that point, you now have a generator with these 5 possible fields. So, any of these operations could be acting on combinations of those, and at this point, it would still keep trying to apply those operations. We don't have any left, so there's only one predicate left, this distinct true. By default, Cascalog will distinct on the output variables. So it adds this distinct in on full name, which cuts everything else out. Basically what that is just group by the thing and like take the first thing of each group. And you end up with this nice graph. This isn't doing anything though. It's just a declaration of intent about the system where each of these operations, like that less than node in the graph, is just a record that holds this function, the inputs that it requires, which in this case would be age and temp1, and also like a list of all the possible outputs that are available at that time. The Hadoop compiler later can like take this data structure and go turn it into what it needs. But you could see how to take this and turn it into an in-memory planner or something else like that. And anything that knows how to talk about these graphs, which are much more familiar, can compile down this data log. We can just plug them in. So that was the question, right? Is like, does any of that look like Hadoop? Like, kind of vaguely, but it looks more like cascading, and really it just looks like a bunch of green circles with lines between them. A lot of the, as I said, like I'm doing this new thing. It's much, much smaller. I'd like to be able to work in the browser. Like, why not be able to code this stuff in ClojureScript or in memory, or use this as a way to prepare data to push into Incanter? There should be no, it's sort of arbitrary to restrict this to Hadoop, and the second version sort of had to go target these other platforms. Akka and Storm are these real-time platforms. That's a really interesting case that I want to get into. So here's this new, as I said, the new picture of the world. The other interesting thing that you can do in Cascalog 2 is it has this pluggable optimization layer. So you can take that graph, which has, is just a declarative structure. It's a zipper. You can go walk it and say at the end of your job you like have 10 fields and then you strip out 8 of them. You should be able to walk the graph and cut out every operation which generated fields that you didn't want. So the ability to kind of fixed point iterate on that logical plan before you pass it into one of these guys is another thing that's quite exciting. So how do you extend this thing? Like, is it a pain in the ass to write a new planner? Like, what does it actually mean to do that? Anyway, these are the three sort of two protocols in the multi-method. This isn't that clean because I was initially kind of trying to like get performance out of this, and what I came to realize is all of this happens, I've been thinking of it as like the second compile time. Like, there's no need for this to be fast. You're prepping a Hadoop job for like a Hadoop cluster, and so, taking as much time as you want to make that clean is great. But anyway, all you have to do to implement a new like platform, to implement the in-memory or the Clojure script or anything like this, is that you need to be able to tell the planner, is something a generator in the world of this platform? Can it produce data? In which case it'll be assigned to one of those generator nodes. Can it filter, which is just a way of resolving if you only have like one set of fields, is it input or output? No problem. And then you also need to be able to convert some operation, one of those first things within the predicates, into a node in the logical graph. Because nothing happens with it, it's just bucketed there. And then the final thing that happens is this plan method. Once Cascalog builds the whole graph, when you call plan, that's the signal to go ahead and turn that logical graph into like a physical plan in Hadoop or something. Often the way those work is you can then use those again as generators. So you can plan is kind of the way to shuttle up and down between the Cascalog level of abstraction and then back down into, say, raw Hadoop, and then back up into Cascalog and down and up and on and on. These are the basics. I sort of fleshed them out for like functions and vars and objects and multifunctions. Can filter, cascading jumps in and says, okay, well, my filter operation is also a first-class operation. You could extend this to Scala functions if you had a mind. Things like this. It's quite easy to build a new platform now, and will become easier, I think, as people start to do it more. Some platforms I've been excited about, I don't quite know, like, I know that this is possible. The Clojure one, no problem. Clojure script, I think nothing in this compiler has anything to do really with the JVM. It's just records and protocols that go walk these graphs. The core async one is interesting. It feels similar to a real-time streaming planner in that your generators could be channels. And if you have some notion of a time window through which like a join can take place with an inner sort of timeout looping channel, the final query could plan down to a channel as well. So you could actually build these data log sort of trees of channels under the hood that make it easy to imagine these like very, very complex flows of data. And then Storm is the big one that I had initially started out trying to target, basically being able to take the same code, run it on Hadoop or run it on Storm. And it looks like that's going to be just fine. And so, yeah, takeaways. Like what's with all this? Number one is like use logic programming. Let the system deal with complexity for you. Like don't try, they say, there's this quote about premature optimization. I think that it's fine to obsess over these things if you're doing it at a systems level where it can be as general as possible. But like ideally you'll let the system do as much of that obsessing as possible so you can share these facts and it makes it easy to abstract. Take advantage of the properties of your data. That's what these facts are. You should be able to throw all these in at the system and have it do work for you as long as it can. And then the final thing I found in a lot of the work at Twitter is people talk a lot about sharing code. You want to share code, you want to run it in the browser, you want to run it here. Really, I think what people are concerned about is sharing data, right? Like you go do a calculation on the Twitter data, you want to produce some notion of word count or follower pairs or things like that. Sharing code means it's calculated exactly the same way. Really, you want this promise that this real-time queue is going to hold the same information as this file system. Like if there are shortcuts you can take on one platform versus another, you should absolutely take them. And I think it's difficult to understand those trade-offs on a case-by-case basis if you're coding at the low level. So trust as much as you can the logic program, and success will follow. That's it. Questions, anybody? Oh, yeah, yeah.
Does Cascalog support recursion?
No, it doesn't support recursion, but I think that's just because I'm not wise enough yet to know really what datalog should be able to support. So, but yeah, that comes up a lot, and I think it's time I just buckled down and read up on how datalog should actually be implemented. And made it happen. Like, I say this is datalog, but it might not be. Like, I think it is. But so maybe we'll chat tonight, and you can school me. Yeah, I can't see that well, so if you have a question, maybe just shout out. So the way that works is you saw that distinct predicate where I had in there. Anything that starts with a keyword and goes to a value is treated as like an option by Cascalog. And let's see if that still showed up. When we go ahead and create a generator, basically like this thing just gets the grab bag of options. So those are all sort of pass through that hit the underlying platform at the end of the day. And effectively like when you add these option predicates in, they only sort of make sense within the scope of that particular like bucket of predicates you gave. So you could say, in Hadoop, it's like, you know, the number of tuples you should aggregate on the map side. But like you said, it could be the timeout, or in, you know, you could have some sort of cache size that you allow, and that all just gets sent right through. Which is very hard for me to imagine how to do in like a type-safe way back in Scala land, but here it's no problem, just anything goes. And it's much easier to sort of communicate through the abstraction layer, I found, for me anyway.
So the datalog queries are essentially, they're creating generators, so I guess they can plug into each other and all that.
That's right.
Have you done much just growing out the theories where it gets too silly with the size of the plans, you know, they call each other and things like that?
I haven't with Cascalog so much. When I was doing some similar work in Scala on this project called Summingbird, and we built a little, I don't know if you're familiar with generative testing, we had sort of generators of possible plans. And some of those could get pretty ridiculous. I found that the complexity of the flows people actually write aren't that enormous and haven't really been an issue. But I mean, trying to make it easy to write really complex things, we're going to hit that. So. That's sort of at the optimizer stage, you should be able to say, this thing looks like it's going to loop, and you know, you've done something wrong for this particular platform.
Can you talk more about the storm target?
Yeah, the storm target is, so there's this, one of the big users of Cascalog is this company called YieldBot, and Soren Macbeth is this great engineer there who's written a Clojure like DSL over top of Trident, which sits on top of Storm. Trident adds in this notion of joins by, like, all the tuples that come off the spouts or off of your queues are assigned to these micro batches, they're called. And that's sort of, those are assigned through some fixed time window. So he's got the Clojure layer already. He hasn't open sourced his stuff yet, but now that I'm like out of Twitter and have a lot of free time, the goal is to go write a platform that will compile down to that. So that actually should be one of the first things that comes out, just because he's got the abstraction so nice up above. And what it would do is plan down to effectively a Trident topology. And then you can go run that using the usual ways that you run Storm. That enables this really interesting thing you can do that Nathan Mars has spoken about a lot, where you take the same Cascalog query, run it on Hadoop, run it on Storm as well, and then have a client that can merge the results together. And that was a lot of the Scala work I was doing over the last year. So I think those ideas will make it over before I forget them. Yeah, I silently released it last week. I haven't. It's out. No, it's done. It's, you know, and the final thing to do, as always, is to just turn this into a blog post and like write out how to flesh things out. Cascalog 2's out, and the big immediate advantages are, I didn't talk about this here, but it supports these serializable anonymous functions. So you can, you know, go just work at the REPL and sort of jam out functions, and Cascalog will figure out how to package all those up and ship them off. I think it's a nice base from which to build these, you know, a future Spark planner or things like this that really need to go serialize logic across, you know, across network boundaries. So it's out, but check out the mailing list, and I'll send out an update in the next day. Yeah?
I know it's old school technology, but are relational databases a reasonable target?
Yeah, they're a pretty reasonable target. I think the Datomic guys would have something to say about how reasonable, you know. And yeah, I think I have the honor of giving the first logic talk of the Clojure conference, but I think this afternoon the Datomic guys are going to give a little more rundown of that. But yeah, I mean that this looks suspiciously like SQL, and in fact they're very, very related. I think it'd be, yeah, a great target. Yeah, it looks kind of like Pig too. Like I thought I was kind of on some new stuff, but not really. It's it's all, you know, it's just how it should look, right? It's like folks have figured this out a long time ago for SQL, and these like SQL optimizers are really good now, but it just hadn't made its way to like. I think the way people are building these MapReduce DSLs, like it's exciting to be able to say like code MapReduce in Mathematica or code it in Clojure or in Scala, that really like laying down the groundwork for, okay, like let's get the abstractions right, let's pick Hadoop as one target, but really we should be providing primitives that can hit other areas that have really thought this stuff through clearly. Like you said, if you can hit SQL, you know, you don't have to write these optimizers, like that'll take care of it at that point. Cool, I think that's it. Thank you guys.